Hi everyone. Today this video is the solution for example 1 of the beam deflection method. So the basic idea of the beam deflection is to find the deflection of a beam. So we're going to define the deflection as y of z. So one of the main things we have to do in this type of exercises is define the axis of the beam. In this case we're going to call z the axis of the beam. So any point of the beam is defined by a coordinate z, and then y of z would mean nothing more than the deflection of the beam. And in this case, we could more or less start sketching this deflection. Should look somewhat like this. And what we're trying to define is this quantity y of z, which again can be valid for any point of z in the beam. To do so, we're going to take something that we call the double integration method. And basically this method starts with another equation that we're going to call the Euler-Bernoulli beam theory. And the Euler-Bernoulli beam theory basically says that the curvature of the beam, which again can be a function of z, is nothing more than the moment divided by EI. And then there's this minus sign here that it's a convention that changes from civil engineering and mechanical engineering. But for our convention that we use in structures, this has a minus sign here. So by this stage, you should start understanding that the double integration method is probably associated with the fact that I'm writing these curvatures. And let's rewrite here that these are called the curvatures of the beam. And the double integration method is nothing more than taking the curvatures and integrating once to get something we're going to call the rotations, and integrating another time to do the deflections. So both of these red arrows would represent an integral, and therefore this is why we call the double integration method. Importantly to define here is that this intermediate step is the rotations of the beam. Now let's copy this figure, and now we can start solving this using the beam deflection method. So first thing we need to define is our axial axis, z, so it's going to be left to right in this case. And then the first thing we need to do is think about the bending moment diagram. In this case, the bending moment diagram will have tension on the top, and will have a maximum here at the support, and then it will be a linear function all the way to 0 at the end of the beam. The support here will have a moment of minus 360, that's 60 times 6, and again this will be a negative moment because we're talking about tension on the top. So the first thing we could do is define the function of the bending moment diagram as minus 360 plus 60z. The logic here is minus 360 will be our y-intercept when z equals 0, and then 60 will be the slope of this bending moment diagram. Okay? Another way you can look into this is, without drawing the bending moment diagram, is just to think about the reactions. If you have a 60 acting on the right side, we know our reactions will be 60 like this on the left, and also a moment like that of 360. If we now think about what would be the moment at a certain distance z, let's say here at this green dot, the moment at z will be the initial moment of 360 that is causing tension on the top. So that's minus 360 because negative moments cause tension on the top. And then the positive 60 times z will cause a moment, let's say here in green, will cause a moment that would bend our structure somewhat like this. And here you can see the 60 will cause tension on the top, therefore will be plus 60z. Okay, so you don't necessarily need the bending moment diagram. You can guess the moment just by looking at the reactions and the forces on the left side of the beam. But okay, now we get our equation for moment either through the bending moment diagram or through the reactions on the left side. And now the next step is to use the equation y double dash of z is equal to minus m divided by EI. Again, the curvatures are equal to the moment divided by EI according to the Euler-Bernoulli theory. Therefore, we can say that our y double dash of z is equal to 360 minus 60z divided by EI. So basically, I'm just replacing m with the equation I just found, and then with a minus sign I need to swap the signs. And now we're going to do our double integration. From y double dash of z, we can find y of z, which is the integral of y double dash of z. So the rotations are the integral of the curvatures. So if we try to integrate this, the 1 over ei can actually get out of the integral, and then we're just going to solve the integral of 360 minus 60 z dz. Therefore, we can rewrite this as 1 over ei and then times 360 z minus 60 z squared over 2 plus, and now let's give it an integration constant, let's call it c. Now we can continue our calculation and get finally the deflection with respect to z, which will be the integral of the rotation with respect to z. So now we can do again 1 over ei. Again, this will be outside of the integral times the integral of the rotation. So that's 360z minus, let's simplify here, 30z squared plus c. So now when we do this integral, we're going to get that the 360z becomes z squared over 2. This will become minus 30z cubed over 3. This plus cz plus d. So c is a constant in the context of rotations, but then when we integrate it again, it becomes a linear function, so cz. So now we finalize this first step of the problem. We found an equation that could describe the deflection of our problem, of our cantilever. But this has a little problem. It has these two values, c and d, that we're going to call the constants of integration. And we need to solve for them to get a final equation. To do that is to apply something we're going to call the boundary conditions. And if we copy down the problem, we can understand the boundary conditions of this structure are given by this support here, by this fixed support. And this gives us two interesting boundary conditions that we can use. The first one is that the rotation, when z equals 0, and again, remember that z goes from left to right in this case, so when z equals 0, we know the rotation has to be 0, and we also know another boundary condition, which is the displacement at z equals 0. Both of them, forgot to write it here, both of them have to be equal to 0. So these two boundary conditions, again, rotation here is 0 and displacement here is 0, gives us two equations for us to find our two variables c and d. So let's substitute. When y dash of z equals 0, that would be taking the equation of y dash, which we can find here, and replace z with 0. So here, if we substitute z with 0, we can see that the rotation when z is 0 is just c divided by ei. So if we go here and replace this with c divided by ei, we get that this has to be equal to 0. Therefore, we can conclude that c is equal to 0. Now, if we do the same logic now in the deflection equation, which is this one that we just wrote, and again we replace z with 0, we're going to get that this deflection, again the initial deflection, is just d divided by ei. And again, if this has to be equal to 0, we can conclude that d is equal to 0. So this finalizes the problem. When we replace c and d with 0, we can say that our deflection of z in this problem is 360z squared divided by 2. So let's just write 180z squared minus 10z cubed, and that's it. And all of this times 1 over ei. So this is the solution to this problem, and that's one way to solve it. Now, there's nothing preventing you to do the z being, instead of being from left to right, to go from right to left. So now I'm going to repeat the same problem, but I'm going to flip the problem now. So I'm going to make the load being on the left side of 60. So now I can say that my axis will still move from left to right, but it's equivalent to say in this problem that we'll move from right to left. But I want you guys to be consistent with the way you solve this type of problems and try always to solve it from left to right. So let's have a look now at this problem and use the same method as before. So if you want to get the moment in this case, the moment is nothing more, let's say, if you want to find the moment here at that red point, you can see the moment will cause tension on the top. So the moment is minus 60 times z. And if you think about this just using the diagram, let's say it would look like this, and there you would get your minus 360. This would still be negative. Now your initial value is 0 when you measure from left to right, and now your slope is minus 60. So the minus 60z makes perfect sense as a moment. So now as you can see, our moment function is different, which therefore will make our deflection function different as well. So let's continue. Let's now write down the curvature. So if the moment is minus 60z, and the curvature is always minus m divided by ei, we can write that this will just be 60z divided by ei. So now we're going to do our integral to do our rotation. And if we do the integral of y double dash of z, we're going to get that this will be 1 over ei, 60z squared over 2 plus c. And same as before, if we want to do the deflection, that will be the integral of the rotations, dz, and therefore this will be 1 over ei, and now assuming that's 30, we're going to get 30z cubed divided by 3 plus cz plus d. Okay, so we finally get our deflection function, and same as before, we need to use boundary conditions to find c and d. But in this particular case, our boundary conditions, if we are drawing the structure the other way around, and we are still measuring z from left to right, our boundary conditions will be not at z equals 0, but at z equals 6. That's the length of this cantilever. So y dash of z equals 6, so the rotation when z equals 6 is 0, and the deflection when z equals 6 is also 0. So now this might take a little bit longer to solve, but it's still possible. So in this first one, we're going to replace z with 6, and we're going to equate it to 0. So our rotation, which is written here, our rotation is 1 over ei times 60 times 6 squared divided by 2 plus c. And so what we get here is that this value has to be equal to 0. So if we solve it now, we're going to get that 1080 divided by ei plus c divided by ei has to be equal to 0. So we can therefore conclude that the ei's will simplify and c will be equal to minus 1080. Okay, so that's that. And now we need to do the same, but for d. So now that we know c is going to be 1080, we're going to apply the same logic, but now for our deflection when z equals 6. So we have that 1 over ei times, so then we're going to do 10 times 6 cubed plus 1080 times 6 plus d equals to 0. Okay? So I'm already replacing c with the value I found from before. This is actually wrong. It needs a minus sign there, not a positive sign. So we're now in a situation to solve for d. So what we're going to get here is 1 over ei times minus 4320 plus d equals to 0. And again, the ei is going to simplify. Therefore, we can say that d is going to be equal to 4320. So we can now finalize our equation and say that y of z is going to be, this equation here we have the second equation with the green box, so 1 over ei times 10z cubed. And now we're going to replace c with minus 1080, so minus 1080z plus 4320. And this will be our equation of deflection. So now we have two equations of deflection for the exact same problem, but just seen with different perspectives. So how can we find out if these are correct or not? Let's try to calculate, for example, the displacement at the tip. So if you zoom in here, you will see that the deflection when z equals 6 will gonna be our maximal deflection. So let's calculate it here. And if we substitute and this equation, so if we replace here y when z equals 6, what we're gonna get is 180 times 6 squared minus 10 times 6 cubed. And all of this times 1 over EI. So if we put this in the calculator, what we get is 4320 divided by EI. And in this case, the fact that it's positive means the deflection is down. Okay, so this is a good sign. We recognize this number. But now, this displacement here at the tip of this bar has to be exactly the same displacement of the tip of this bar. So this displacement here has to be the exact same. So let's try this out with this new equation. If we want to find the displacement at the tip, that's when z is equal to 0. So what do we get when we do that? This simplifies and that also simplifies. So we just get 4320 divided by EI. And again, down it's positive. So the information we're getting here is there's many ways you can solve this type of structures. You can solve them left to right, right to left. So my suggestion is solve it always left to right, but know if you want to solve it right to left, it gives you the same answer, it's just written with different equations. So I hope you enjoyed this video. I just have one final challenge for you. If you go on Google, you can find tables such like this one that can tell you the equations for different loads and for different spans. So if you go on Google, you'll see that for a load P and a span L, so P and L, the maximum deflection is PL cubed over 3EI. So in our case, we could test by replacing P with 60 and L with 6. And hopefully this will give us our 4320, which it does. So my challenge for you is try to derive the equation for the deflection for any generic load P and for any span L. So if you can't read, this equation is Px squared divided by 6EI, and that's times 3L minus X. So following these principles we covered in this video, you should be able to derive this much more powerful equation since it solves all the cantilevers. So thank you for watching and have a nice day.